In section 9.8, we're going to work on comparing the three major types of equations we've been working on so far: linear functions, exponential functions, and quadratic functions. Those are our vocabulary terms, so we would assume that by now you know what all of those things are and what they look like. But as a quick reminder, linear functions are in the form y equals mx plus b. Their graph creates a line. Exponential functions are in the form y equals a times b to the x power. Again, it's exponential because the variable is an exponent. And they create a curve that is connected with a horizontal piece of line and a vertical piece of line. You could almost think of it as, it's kind of like if I took one end of a quadratic function and bent the end flat. And a quadratic function is a base form y equals ax squared plus bx plus c, and its graph creates a parabola. So if we wanted to take a look at what our function is like by using ordered pairs, one of the things we might do is we might go ahead and graph the ordered pairs and see what we get. So let's go ahead and do that. And I'm going to go ahead and drop in a couple axes here. So let's go ahead and go there and there. And if I go ahead and graph these points at negative 5, 1, negative 1, 1, 2, 3, 4, 5 there. Negative 3, 0, 1, 2, 3, 0. Negative 1, 1. 1, 2. And 1, 2, 3. 3, you can see that it looks like this just might be a line. Right? If I take a look at that, it looks indeed like it might be a line. Okay, if I wanted to go ahead and double check, I might want to look at creating the equation of this line. And I could do that by selecting 2 points. I'm going to select the 2 middle points. So I'm going to use negative 1, 1, and I'm going to use 1, 2. So I'm going to use these 2 points. And if I go ahead and create the equation, I'm going to first find the slope. So the slope would be y2 minus y1, or 2 minus 1, over 1 minus negative 1. So that'd be a slope of 1/2. And let's see if that's really the way it works, right, as we go from point to point. If I go up 1, over 2, up 1, over 2, down 1, left 2, down 1, left 2, I'm not even going to bother writing the equation. I can see that this follows a very consistent slope all the way through. Okay, and if we look at how we might do that another way, is we could look at what are we trying to find. We're examining the y's and determining with an individual change in x, what's the change in y? This assumes that I have, you'll notice I have x values that are negative 1, 0, 1, 2, negative 1, 0, 1, 2. They are consecutive, okay, or sequential numbers. If I have sequential x values, then I can examine the y values to find the difference. Okay, so you'll notice that in the case of a linear function, 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3. That means that for every change in x, I have the same change in y, and that's what we would call the slope. Now that's not true when we look at an exponential function, and instead what we get is that when we divide, so 0.5 divided by 0.25 is 2, 1 divided by 1/2 is 2, 2 divided by 1 is 2. We have a common ratio. So this is a common difference. A common ratio is a sign of an exponential function. And when we look at a quadratic function, see, the quadratic function doesn't have the same difference in the first set, but if I find the differences between the differences, negative 1 minus negative 3 is 2. 1 minus negative 1 is 2. 3 minus 1 is 2. The second level differences show that it's a quadratic function, and that's because it's a second degree function. Guess what would be the same in a third degree function? The third level differences. And in a fourth degree function, the fourth level differences would be the same. So this is one way that we can use an input-output table and categorize different types of polynomials to tell what they were. So let's take a look at that in action. So if I wanted to check, first I'm going to check differences. I always find it's easier. So if I have negative 1 minus negative 4, the difference between these guys, negative 1 minus negative 4, is 3. Between 0 and negative 1 is 1. Okay, well, obviously that's not right, right? Between negative 1 and 0 is 1. And between negative 4 and, between negative 1 and 0 is negative 1, and this becomes negative 3. If I went ahead and look for my second level differences, 1 minus 3 is negative 2. Negative 1 minus 1 is negative 2. Negative 3 minus negative 1 is negative 2. So this is second level differences match up, so this is a quadratic function. Okay, so my first level differences didn't match, but my second level differences do. And then the next thing I would have tried would have been move on to the ratio to see if that worked. But you can often tell when you're looking at things, what is it? If we look at this for differences, 4 minus 16 is negative 12, 1 minus 4 is negative 3, 1/4 minus 1 is negative 3/4. You'll notice how my differences are descending. You notice how these mirrored each other, but these are just straight descending. If I look at second level differences, negative 3 minus negative 12 is 9. Negative 3/4 minus negative 3 is 2 1/4. So differences aren't going to get me there with these. It isn't following a pattern what that's going to work out. But if I have 4 divided by 16, that's 1/4. 1 divided by 4 is 1/4. 1/4 divided by 1 is 1/4. And 1/16 divided by 1/4, which is the same as multiplying it by 4, is 1/4. So this is exponential because I had common ratios. Okay, so remember, if I have a common difference on the first level, it's linear. On the second level, it's quadratic. On the third level, it would be cubic, fourth level, quartic, and so on. If I don't have common differences, but instead I have a common ratio, now we're talking about an exponential function. Okay, so linear functions, first level differences are the same, quadratic second level differences. Exponential function, it's a ratio, not a difference. Okay, so if we want to go ahead and write an equation, we can do that with this sort of problem. And what we can do is we can start looking at what type of function is this? Okay, so it might be easier to go ahead and make this as a table so that we can do it the way we were doing it before to start to get a sense of what type of a function this is. So I have negative 1, 0, 1, 2, 3. That's good. I have sequential x values. Remember, that's essential that I have sequential x values in order to do this work. And if I look at differences, 0 minus 4 is negative 4, 4 minus 0 is 4, 16 minus 4 is 12, okay, and 36 minus 16 is 20. That doesn't work. Let's try the second level differences. 4 minus negative 4 is 8, 12 minus 4 is 8, 20 minus 12 is 8. Okay, okay. So second level differences, this is going to be a quadratic function. Okay, so it says here that if we're going to work with a quadratic function, we're going to work with the parent function, y is equal to a times x squared. So we can go ahead and create a quadratic system, right? So what's easiest is that, well, I may not want to use 0. I was going to say 0, 0, but let's use 1 and 4. So I know that 4 was equal to a times 1 squared. So if I go ahead and divide by 1, I get a is equal to 4. So theoretically, we have y is equal to 4x squared. Let's double check some of our values to make sure that's correct. So negative 1 squared is 1 times 4 is 4. 0 squared is 0 times 4 is 0. 1 squared is 1 times 4 is 4. 2 squared is 4 times 4 is 16. So yeah, this is our equation, and that totally checks out. Okay, under other circumstances, for instance, if I were going to use the full form of the quadratic function, I would need a little more information. Okay, looking at solving a multi-step problem, tell whether the data can be modeled by a linear function, an exponential function, or a quadratic function, then write an equation for the function. So if I want to solve this problem, one of the first things I would want to do would be to look at what type of a function is this? So if I look at 57.1 minus 51.4, well, that's 5.7. And 63.3 minus 67.1, that's 6.2. So we're not getting a common difference here. If I look at doing a common ratio, I'm going to pull out a calculator. And if I have 57.1 divided by 51.4, that's 1.11. And if I have 63.3 divided by 57.1, that's actually 1.11. If I have 70.3 divided by 63.3, that's 1.11. So I can see now that my ratio is 1.11, and that means that it is an exponential function. Okay, if I wanted to graph the data, I could do that. And that might also help me because I could look at the shape of the output, right? So that might be very helpful. So if we look at going ahead and graphing the data, let's see what that looks like. And let's say that this is 2, 4, 6, 8, 10, 2, 4, 6, 8, 20 is right there. 2, 4, 6, 8, 10, 30 is right there. Let's see, 2, 4, 6, 8, 10. Oh, I didn't really help for that, did I? So let's do 5, 10, 15, 20, 30, 40, 50. And over here, let's say that we begin at, let's say this is 20, 21, 22. So we'll just go singles across. So let's see, 60 and 70, that should be enough. So at 20, we're at 51.4. That's about here. At 21, we're at 57.1. 22, 63.3. 23, we're at 70.3. 24, we're at 78, so that's almost up here. It doesn't really look like it's following a linear pattern. Okay, so it's very difficult to tell on this kind of a rough graph. It would have looked better maybe if I'd put it in a graphing tool. But because I've already figured out the ratio, I know that this is an exponential function that's going to go ahead and have a curve to it. So let's go ahead and write the equation. So we decided it was exponential. And if we want to write the equation, then let's go ahead and pull some of the points. So let's do 20 and 51.4. And let's pull 21 and 57.1. 57.1. Okay, and remember that we already knew that our ratio was 1.11. So I know that I'm working in this form, y is equal to a times b to the x power, and the b is 1.11. So I have a times 1.11 to the x power. And if I go ahead and plug in these values, I know that y was 51.4 when x was 20. Okay, and it doesn't look like I'm actually going to need a second point here. If I go ahead and take 1.11 to the 20th power, it comes 8.06. I'm going to invert that and multiply it times 51.4, which is the same as dividing. 51.4 equals, and I get 6.375. Okay, so y would be equal to 6.375 times 1.11 to the x power. And that's how we go ahead and take that table, identify what type of function it was, and then write the equation that models the data.